Okay, so we have just seen how to find parameters of linear regression analytically. This was a very long, very technical lecture, so I hope that you got through it in the end. This, from now on, it's going to be easier, I promise. So we're going to talk about forms of linear regression now. So we tried this model, right? So, and we found that the coefficient at newspaper beta3 is probably just 0, right? So maybe it shouldn't even appear in the true model, right? So so let us try the true model with just 2 predictors. So the budget for TV and the budget for radio campaign, and we want to predict the sales of our product. So let us do it in R, and this is what it looks like in R. Let me explain what this means, right? So we have these coefficients. Yeah, this is the summary function of in R. So first I trained a linear model, and then I looked at the summary of this linear model. Now, if I believe, it means the following. It means that if I believe that the true model is linear, that sales depends on TV and radio budgets in a linear manner, then this statistical significance in 3 stars here, here, and here means that there is a very, very low probability to observe positive numbers here if the true values here were negative. So in other words, we can be absolutely sure that if the linear model is correct, then the true value of intercept of the coefficient at TV and the coefficient at radio are actually positive. So they may not be exactly as these ones, so slightly different, slightly off, because we can only do so good as to infer, these values from data. But they are definitely positive. That we can know, but only if we believe that the true model is linear. Because maybe we think a little bit about it and realize that, wow, it doesn't really make sense that, our sales grow linearly with the budget always. Because if this were true, it would be too good to be true. So imagine that we only have a certain market to work with, right? So, and of course, our sales cannot be more than our market value. So it doesn't make sense. So it's impossible to pay too much for ad, and just always get everything. So something in return. So which is, maybe we can try something more complex, something like a quadratic model. So we are going to introduce more terms. So it really means that we're still doing linear regression, but with more variables, right? So if these TV and radio are our original variables, so these are like x, x1 and x2, then TV squared, so is going to be our x3, TV times radio is going to be our x4, and radio squared is going to be our x5. It's still a linear model, but with more variables, right? So this is a polynomial regression, but as a matter of fact, it is still a linear model. So this is what it looks like in R, right? So this is how I fit it. You're going to do it in the lab, don't worry. And below is the summary. Okay, so, and now we see that it makes sense, right? So what it tells us is that the coefficient at TV square is negative, right? So it means that with a fixed budget for radio, if we just look at the outcome of our campaign as a function of TV, of the budget for TV, then it is a quadratic function with a negative coefficient at the quadratic term, right? So it looks like a parabola upside down. So this is our sales, and this is our TV budget. But then it makes perfect sense, right? So because we see now that regardless of the value of our budget for radio, so the sales are going to grow. So the more at first until to a certain point, and then it's going to stop growing. What I'm trying to say here is that we can interpret this model. It makes perfect sense. While at the same time, so notice that the coefficient at radius squared is not statistically significant, which means that the true value, for all we know, could be positive, could be negative, we don't know, right? But the funny thing about it is that if we just delete it from our model and redo our model, then the statistical significance could change. So after we remove it, variables that were statistically significant could become insignificant and even weirder. So if we add more terms, like if we add, I don't know, TV cubed here, then suddenly radius squared could become statistically significant. So which is why coming up with a good linear model is something like a dark art. I mean, there is no like well-defined procedure to do it, to always find the answer. Right? So, and I mean, if you think about, so what if the true model includes terms of degree 3, I don't know, 4, 5, and so on. So where do we stop? Basically, the idea here is that you just need to look for meaning. So if you can interpret this polynomial regression, then so be it. So go ahead with this. But if you cannot interpret it really, so if you add too many terms of degree 3, 4, and 5, to the extent where it is just not interpretable anymore, then what you should do, you basically should just forget about trying to interpret it, and you just treat it as a regression problem with just a lot of predictors, and you apply some regularization methods. Or maybe even better, you just don't do linear regression at all, and you do some other like support vector machine or random forest or artificial neural networks that we are going to learn a bit later in the course. So another common modification of linear regression is log linear model. This is what it looks like. So log linear means that instead of regressing the original variable, so we take its logarithm and then we construct a linear model for the logarithm. Now, in the lab, we're going to try it. So to predict property prices in Singapore, this is actually a very common popular model for property prices. So that's basically it. So now, please do this little quiz.